So today we're doing DP runtime optimization. Now it starts in gold, but it also goes well into platinum. Most DP problems in platinum have some sort of optimization, or it's hard to come up with the DP state. So DP runtime optimization is something that shows up quite often. Now I want to review something real quick from the basic DP lecture that we did a few weeks ago. Let me just share my screen here. Okay, so if you recall, the runtime for DP is number of states times number of transitions, or sorry, transitions per state times runtime of each transition. So again, this lecture presumes that you've already sort of watched the how to solve any DP problem lecture from a while ago, or at least you're familiar with DP a little bit. But I just want to give you an idea of exactly what my formula thing is. It'll just take a couple minutes, but that way we can all be on the same page. So let's say, for example, I'm trying to find the ith Fibonacci number. So let me share my screen here. Cool. I like to share my screen of a note rather than just using a whiteboard because the whiteboard people get lost all over the place. So we're just going to use this. All right, so let's say that we're trying to find the ith Fibonacci number, right? Why does it keep doing that to me? So you all are probably familiar with this, I'm guessing. If you've done DP before, it's usually the standard problem that people use. So you just have, DP of 1 equals 1, DP of 2 equals 1. So like DP of I equals or try to find the nth Fibonacci number, let's just say, and DP of I equals the ith Fibonacci number. So DP of 1 is the first Fibonacci number, which is 1. DP of 2 second Fibonacci number is 2. And in general, DP of I equals DP I minus 1 plus DP of I minus 2. So this is going to be our state. This is going to be our transition. This is going to be our start states. And then our answer is going to be DP of n. So pretty straightforward here. So this is our state definition. Now, when we calculate runtime, recall that the formula for runtime, oops, let's make this bigger so that we can actually see it, is going to be number of states times number of transitions per state times runtime per transition. So in this case here, our number of states is going to be n. We have n states in our DP array. Transitions per state, well, there's just one transition that we can see here. Times runtime per transition. Well, the transition has two things that we're adding, so we've got to find these two values. Times 2 equals O of n. So this is the basic formula for our DP that we're going to use. Now, this is just to give you an all definition of how we're doing DP, and you start to get into the more complicated problems. So, in order to optimize our DP, right, now that gold problems are getting harder, you're going to see some gold problems, and especially platinum problems, but quite a few gold problems, we're just coming up with a DP is no longer sufficient. You have to come up with a DP that runs in time. That means you have to optimize one or more of these parts here and speed it up in order to get DP to run faster. So, the first problem that we are going to work on is called Pogo Cow, and I am going to put the link in the chat and give you guys a minute to read it. So I'm going to put the link in the chat. All right, link is in the chat, and I'm also going to share screen with it so that you guys are able to read it real quick. So I'm going to give you a couple minutes to read this problem here. All right, I am going to hope that most of you have read this by now. And we'll get into discussing it. So the first thing is that Bessie is only allowed to move in one direction, and she can start at any target of her choosing. So she can either move left to right, or she can move right to left. So we're going to solve the problem for the case where she moves left to right. And in order to do right to left, just literally do the exact same thing but backwards. So like if you know how to solve it for left to right, just reverse all the points and you can do the exact same thing backwards to get the solution for right to left, or just do the algorithm backwards. It's pretty similar. The hard part is how do we solve this for left to right? So this is a DP lecture, so you can probably assume that this is going to be a DP problem. So let's start working on this. And I'm just going to draw straight on the screen. Okay, so we first need our DP state. So what probably makes sense is we need the current location that Bessie is at. Let's call this index of current target. Okay, now that's not going to be sufficient because just because we know the index of our current target, we don't know how far we have to hop to the right, right? Because each hop must cover at least as much distance from the previous hop and must land on a target. So if the previous hop was like really tiny, then we have to only hop a tiny amount. Then like we're only required to hop a tiny amount. But if the previous amount was large, a lot of our potential hops might not be valid. So we're gonna add size of previous hop. Cool, and this is gonna equal this is gonna equal max points. And assuming that we land on the current index. So we're gonna assume that we land on this current target here. Okay, so now that we have our sort of DP state, right, the next thing we're gonna need is our transitions. So how do we calculate dpij? Well, let's not look at it in terms of calculating dpij, because for this problem, that might be a little tricky. Let's look at from dpij, where can we go next? Like what states does dpij update? So next we can go to dpk, and then like location, the last jump was location k minus location of I, assuming we sort the pads in order. If the jump to location k is far enough. So if location k minus location I is greater than j, or 2 times j. It says at least as much, so yeah, it's greater than or equal to 2 times j. All right, and let me just pick a little bit better color here. All right, so we have our DP state, right? So actually, you know what? Let's just like stop here and then we'll just share to a we'll just share to an empty text document. Might be easier to read. Okay. Shouldn't we use one more state? 0, 1 for L to R or R to L. So for right now, we're assuming we only do L to R, and then we'll just do a second DP backwards to do R to L. So it's a good question. But yeah, for right now, we're just gonna solve the problem, assuming we're only doing L to R, and then at the end, literally just do the same thing again backwards for R to L. It's the same problem either way. Okay. So we have our DP state. So our transitions, so for every DP state, we go like So yeah, we do this state. If the distance between the new state we're hopping to and the old state is at least twice the previous jump. But it's not just going to be one value of k, right? So we can say for all k such that it's true. So now we're going to have there's going to be O of n such k. So now when we calculate our runtime, all right, our runtime number of states. So index of the current target is going to be n times size of the previous hop. Well, the hops are at target locations in the range of 0 to 10 to the power of 6. So n times 10 to the power of 6. This is going to be our number of states times number of transitions per state. Well, every state goes to n other states. So O of n transitions times runtime of each transition. Luckily, this transition is just O of 1. Now you might be saying, Ria, in order to check if this is true, we can do this check in O of 1 for a given k. So that's not bad. Okay, now the problem here is that n equals 1,000. So our runtime is O of 10 to the power of 12. And that's way too slow. We need a lot faster runtime. So in order to optimize it, we have to optimize this, this, or this. There's only 3 options. Now, runtime of each transition is already O of 1. So we don't even have to worry about that. That's just going to be, that's just only going to be O of 1. We can't optimize that. Let's see if we can try to optimize the number of states. So let's look at the second variable here, size of the previous hop. Now, notice that the previous hop must have come from a previous lily pad, or not pad, the previous target. There's a similar problem with lily pads, but previous target. So if these are our current targets, and this is index I, so where we're currently at. The size of the previous hop cannot be this, cannot be this, cannot be this, can be this, can be this. There's a whole bunch of targets that the values of sizes that are invalid, and only very few values of sizes that are actually valid. So a lot of these values here are being not used, and that's good for us, because if we can remove the values that are not being used, we can speed up the runtime. Specifically, the only possible values for sizes the previous hop means that we're coming from a previous lily pad. So what we're going to do is we're going to change this to be index of previous target, not lily pad. Okay, so we have our current lily pad, our current target, and the previous target. And now dpij, so we have our current target, we have a previous target that we came from. So our the next target's k, the previous one we came from is just going to be I. Right? For all k such that the new distance is still going to be log k minus log of I, the location of the 2 targets. Except now it's going to be if it's greater than or equal to 2 times the previous distance, which is log I minus log j. I believe the problem calls target i's at position x of I, and it gives you points worth p of I. So it's going to be this plus points of k. All right. So now our runtime has sped up a little bit. So our number of states, why is it 2? Why is what 2? Oh, the 2 here? So the problem said is, oh, I see. It says each hop must cover at least as much as the previous hop. Good catch. It's not at least twice as much. All right. My bad. Good catch, Saber. That. Yes, it should just be log I minus log j. And the same is true from the previous DP state we did. It should just be log I minus log j. So this makes sure that the current jump is at least as much distance as the previous hop and lands on a target. Perfect. All right. So now, what is our current runtime going to be? Well, let's calculate this again. Number of states is going to be n instead of times 10 to the power 6. It's going to be n times n. But this is the same number of transitions, same number of runtime per transition. So now our runtime goes down from 10 to the power of 12 to 10 to the power of 9. This is significantly faster. So that's a pretty good starting point. So the thing is, 10 to the power of 9 is still going to be a little too slow for this problem, just a tad bit. And so we have to speed this up a little bit more. Now, how do we speed this up a little bit more? Well, let's try. So currently, for every state dpij, we've listed the new states it can update. Right? So it's gonna be like a range of states to the right. Let's try shifting it around so that for every state dpij, we keep track of all the of the states that it came from. So instead of using ij to update a previous state, let's try to figure out how do we calculate dpij from previous states. Okay, we're trying to calculate dpij. Like, what's the possible transition it could have come from? Well, it's going to be dp. Let's say it has to come from j, right? Because we know the previous state was j, so the previous one has to be dpj, and let's just say k, some k before j. Plus points of I, because we're heading in the new point I. So dpjk plus points of I, for all k, such that it's within range. So that's going to be log of I minus log of j is going to be greater than or equal to log of j minus log of k. Cool. So now, basically what we're trying to do, because we're trying to find the maximum number of points, right? So what we can actually do is we can just find the max value of dpjk and then add points I to it at the end. So we can just say points I plus the max value of dpjk for all k such that this is true. So that's all we need. We just need to find this this max value. Okay. Now the runtime, notice it's still n cubed. We still have n squared states. We still are doing O of n transitions per state. We have not yet sped up the runtime, but we're going to use the switch we make in order to speed up the runtime. And here's how. So let's say for calculating dpij, we take the max of all of these. Like, all right, cool. And now we're looking at dp I j minus 1. So here's the thing about dp I j minus 1. Because we're looking at the locations in sorted order, we're sorting all the locations. Log of I minus log of j is just gonna minus log of j minus 1 is just gonna get bigger. Like the biggest, the latest jump is bigger. So this means there are more possible value of k's. So all the possible value of k's that were valid for dpij are also going to be valid for dpij minus 1. So when we're calculating dpij minus 1, we don't have to recalculate all the values of k that we already decided were valid for dpij. Right? So if we think about this in terms of a bunch of items in an array. And this is I, and this is j. And let's say these are the possible k. Notice that the possible k are going to form a consecutive subsequence behind j. Right? It's impossible for these to be the possible k and not these ones. So the possible k has to be right before j because we want this jump to be smaller than this jump. This jump should be greater than this jump here. So they have to be very close to j. So now, when we look at j minus 1 here with the same value of I, the set of possible k gets bigger. Right? It's impossible for the set of possible k to be smaller than this blue box here. Even if the blue box, let's just say the blue box was a little bit bigger, so that just to make it a little clearer. Now these are the possible j. Now, yes, we're not counting the current value. K K could not equal J unless that's just the one we're starting out at. And we're going to talk about start states in a moment, so don't worry about that yet. But yes, we're removing the current value, but other than that, we're only adding values to possible values of K. Okay, so because of this, instead of having to redo work, what we can do is we can just keep like a running maximum of these and keep adding the new values to the max. Then we'll look at J minus 2, we'll just add some new values to the max. And instead of having to look over these new values every time, we'll look over them once for DPI. So we don't look at the same value twice, like the same range twice. And for that reason, we can now calculate our transitions in O of n for a given value of I, and our overall runtime is now going to be over n squared instead of n cubed. All right, any questions about this runtime optimization? Cool. I do want to talk about start state and end state just because I feel like it might not be super clear for this problem. So for this problem, start state basically means that you start on a given pad. So the previous distance you've jumped is 0. So the new distance can be as tiny as you want to. So I would just say start state dpxx equals points of x. That's just what I would consider as the start state. For all x. For answer state, I would just say max value of any dpij. Because you can end anywhere. So, and we don't know what, and the previous jump can be anything. So I would just take the max value of dpij. Cool. And that basically covers this DP problem. All right. Any last questions about this problem before we move on to the next one? Awesome. All right, so I put the next problem in the chat. Feel free to actually, yeah, read it real quick, and then we'll start going over it. This is a very small problem statement, so hopefully it won't take too long to read. But it is quite a difficult problem. All right, so let's talk about this problem here. Stamp painting. Okay, so at this time, this was one of the difficult problems in this gold contest, so I think it's a good one to go over, especially because the DP problems are actually getting a little trickier since then. So, perfect, white's visible here. Oops. Maybe if I bold this, it'll be even more visible. Okay, so let me bold it. All right, so DP, we need a DP state here because you already know this is going to be a DP problem. Just to review the problem, we have an n-length canvas, like a 1D line of things of length n, and she has m stamps, or like stamps of m different colors, and a stamp is k units wide. So for the sample input output, as you can take a look down here, the thing is of length 3, and she has 2 stamps, each of which are 2 units wide. All the stamps are the same length. You can place AAA, AAB, ABB, and BAA, BBA, and BBB. Okay, so we want to know how many different ways are there to make a painting. And notice that you can see like a subtask here. The subtask n and k are less than or equal to 10 to the power 3. So now that we've gone over one problem, I'm gonna give you guys a chance to actually try to like figure out the basic DP. So if anyone has any ideas for a DP state, drop it in the chat. Or unmute yourself and say it, either way. Okay, so the first thing to sort of notice is I see one comment here. It's close, pretty close. But not quite. So the first thing to notice is like let's say we have a bunch of these like locations and we're trying to paint them. And k equals 3. Regardless of how many paint sizes we have, like let's say we have a paint which is like painting like AAA, and then like these get updated to like BBB, and then this becomes like CC, and then this becomes like BB or something. Right? Notice there's the last stamp. The last stamp that we paint is still going to be completely visible. So in the last stamp is going to be k units wide. So we have to have at least one stamp of length k that is visible. So somewhere in the entire thing, we have to have something of length k that is visible. Now, it's guaranteed that like k is less than or equal to n, right? So if k equals n, this is a good problem solving skill, like asking yourself some like sub-problems. So what's the sub-problem of k equals n? Then what's your answer? Well, then your answer is just going to be n. For every color, you can use it to paint the entire thing in just one stamp. Cool. But now we have this case where k is less than or equal to m. So now we have this weird situation where we can paint, like we have the final stamp somewhere. So somewhere in this entire thing, you're going to have something of like a sequence of length k. But around it, you might have different stuff, right? Like let's say I have CCC here. I might just have a B here because it's possible for this to be B and then the rest of it to be C. So actually, what turns out to be the case is like you literally can have literally anything else anywhere else as long as you have one sequence of length k somewhere in the array. Any questions about this? Great. Okay. Actually, that was very short. Great. If you have questions, please throw them in the chat, and I will definitely keep getting to them. So we just need to count the ways to put a sequence of length k into the answer. So like, let's just say we did some straightforward math, right? We said, okay, the sequence can have a starting location of like n minus k plus 1 starting locations. So the sequence can start in any of these locations. And then for each starting location, we have m possible colors for that sequence. Right? Okay. This seems possible. The issue with this is that it's going to double count a lot of possibilities. So let's say we had CCC, BBB. This is going to be counted twice. One where CCC shows up and one where BBB shows up. And so counting this is going to be very tricky. So we're going to use a technique called counting the opposite. So we're going to first start off, like, so we know that there has to be at least one sequence of length k there. But this is proving pretty difficult to find at least one sequence of length k. So what we're going to do is we're going to count all possible sequences. Then we're going to subtract sequences that do not have a continuous range of length k. Move this DP down. This equals the number of sequences with at least one range of length k. And this makes sure that we don't overcount. So we're saying all possible sequences minus the ones that have 0 continuous ranges of length k. And this is going to equal the exact answer that we want. Cool. So now our DP is a lot simpler. Now our DP just has to count how many sequences do not have a continuous length of range k. So we can start with something like DP index length of continuous sequence and last color equals number of ways to make that sequence with no range of length k. All right, I'm going to pause here for a second and take questions. Any questions about anything we've done so far? Perfect. All right, let me copy this over to a whiteboard, and then we'll just do it there instead, because it might be a little easier to read than trying to. So this would be 1E9 states. This is way too many states. We're going to optimize our number of states in a second. But yes, this is definitely way too many states. All right. So copied it over here. All right, so let's calculate the number of states and the runtime actually. So seems like someone put in the chat 1E9 states. Let's verify this. So DP, what is the index? How many indexes are there? There's going to be n. Length of the last continuous sequence, this has to be less than or equal to k. And the color of the last one, m. This many states. So it's going to be 1E9 for the 75% of cases where n and k is less than or equal to 10 to the power 3. However, it's going to be 10 to the power 6 cubed. That's 1E18 states for the general case. That's going to be a lot of states. Okay, before we optimize this, let's just do transitions. So, DP, I, J, K. So you got two options, right? Or transitions are basically the options of things we can do. Paint the same color. So you go to DP, I plus 1, J plus 1, and then the last color stays the same. And you can only do this if J plus 1 is less than K. Or paint a different color. So we're going to DP I plus 1. The length of the last sequence is going to be 1. The last color can basically... Oh, I should pick a color. Let me pick M here, because K is already used in the problem. So we're going to... Oh, M is also used in the problem. Let's use P. All right, let me turn my phone off real quick. All right, there we go. Okay, so the last color can basically be any color except for P. So this is going to be O of M transitions. All right, and we're going to do both. So our runtime is going to be O of number of states. That's going to be N times M, K times M, times number of transitions per state. That's going to be O of M. Times runtime per transition. That's going to be O of 1. This is going to be a really large runtime. Okay. Now, what if we were just to remove this last dimension? And we say number of ways to make that sequence with no range of length k, given that the last index can be any color that you want it to be. Or like, the last index can be all possible colors. So if we can remove this dimension, we'll remove an entire M from our state. That would be amazing. So let's try it. How do we do our transitions? DPIJ. If we paint the same color, we're going to go to DPI plus 1J. If we paint a different color, we're going to try all colors except for P. So we're going to go to DPI plus 1, 1. And we're going to say, like, this is going to plus equal DPIJ times M minus 1. This is going to plus equal DPIJ. So let's look at what these two transitions are doing. We're going to say dp I plus 1, j plus 1. So we're going to basically saying that dp ij is going to equal to, or sorry, it's going to update if we just increase the sequence length by 1. And here, it's going to update the case if we pick a different color. All right, so this would be symmetric. Solve for one color, then we can multiply by m minus 1. Exactly, we're just multiplying this by m minus 1 here. Cool. What is our new runtime? Well, our number of states has dropped by an m, n times k states. Our runtime, so our number of states is going to be, so we have n times k states, and our transitions has now gone down from O of m to O of 1. And our runtime for transition is also O of 1. So we got rid of this m and this m. We got rid of 2 and 1. Cool. We have O of n times k runtime now. That's pretty great. And this will solve these. It says 75% of test cases have n and k less than or equal to 10 to the power 3. This will solve those 10 to the power of 3 cases. Perfect. Okay, now let's go for the full solve. So for the full solve, this is still going to be a little bit too slow. So what do we do about this? Well, we're going to apply the same technique we did to Pogo Cow. So currently for dpij, we have calculated the next state that it can go to, right? It's either dpi plus 1, j plus 1, or dpi plus 1, 1. Let's calculate it backwards. Let's try to see how do we sum up dpij. How do we calculate dpij? So let's first calculate dpi0 is impossible, right? dpi1, so we have one of the current, this is because like we've always had one of the current sequence at least. So dpi1, we've had one of the current sequences. This is this case here, where we're currently painting a different color than was any time before painted. So this means we have dpi minus 1. We're going to do all possible values of j. So j, actually let's just use a different value. J, or 0 less than, I guess 1 less than equal to p, less than equal to k. Sum of this for all p. So, oops, for all p here. So for the previous, at the previous index, we could have tried any possible value of k. And this would work. Okay. Now let's calculate dp ij for a value of j that's not k. This is literally just going to be dp I minus 1, j minus 1. Cool. So with this, we have we solved the problem, but there's a slight issue with doing it forward like this, right? If we do it this way, and I'm like, all right, let's calculate the runtime now. Well, number of states is going to be n squared, and number of transitions per state is, I guess, technically 2, but runtime per transition, this transition is going to take O of k. So it's going to be n squared k for the exact same algorithm, which was n times k here. So whenever you're doing a DP, try both. One might be faster than the other, and you do not want to lose points because you did it the wrong way. Now, we can actually calculate this faster using prefix sums. So if we use prefix sums, we can calculate this in O of 1. And just sum up all the, like... Actually, hold on a second. We don't even need prefix sums. I'm going to take this back. If we don't use prefix sums, notice that this happens for one... For O of k transitions, the runtime is O of 1. For one transition, the runtime is O of k. So we can just analyze our runtime a little bit faster, right? A little bit better. So our runtime is number of states times number of transitions per state times runtime for each transition. So for every single transition, we can calculate this product separately. So number of states is n squared. Okay. Now let's do transition times runtime per transition. So for one transition, the runtime is k. For k transitions, the runtime is 1. And we're doing this for, should be n times, because we're doing this for every I. So for all the values of j, we're calculating this separately. So our runtime here is going to be O of n times k. Cool. So now we want to speed this up a little bit. And we want to get this to run in ideally something much faster, right? So okay, so we have to do these two transitions a lot faster. Now, notice the issue that we currently have. The issue is not our transitions, right? It's 1 times 1. The issue is our number of states. So if we want to speed up this problem, we have to somehow find a way to reduce the number of states. And I mean, it doesn't make sense to reduce index, so we have to reduce the length of the continuous sequence. Okay, so let's remove this. Now we just have dp index. And we have to make this change because if we keep this second state here, it's going to be impossible for us to get a working solution. So let's remove this. So now, how do we ensure that there's no range of length k? We were using that second dimension to ensure there's no range of length k. So now we have to basically change up our entire dp. So dpi, how do I calculate this? What we're going to do is we're going to say that we're going to start at a different state j, and we're just going to add a sequence, add the same color from j plus 1 to I. So this looks like dpi is going to plus equals to like, or sum of all dpj plus the number of colors we can choose to add is m minus 1. So it's going to try times m minus 1. So for each of these dpj options, we're going to have n minus 1 things that we can add after. And we want to make sure that this latest sequence is of no larger than length k. So we're going to take it for such that I minus j is like greater than k. Sorry, less than, yeah, greater than k. No, less than k. So if k equals 1, then I and j like, oh, sorry, less than k. So if k equals 1, then j literally has to be the previous element. Okay, so notice that we can rewrite this as like dpi equals m minus 1 times sum of all dpj for I minus j is less than or equal to k. And we can like change I minus j less than or equal to k. It's like we can move j to the right by adding j here. And we can just subtract k here. So I minus k is less than or equal to j. And so the runtime here is dp of, or sorry, of number of states is n. The transition per state is going to be like 1 times runtime per transition. This takes n. Or sorry, k. We can speed this up using prefix sums. So we can calculate prefix sums to take the sum of this in O of 1. This is going to be O of n runtime. And now we solve this problem in O of n. So we've gone from O of 10 to the power 18 to O of like n, which is pretty cool. All right, that's it for this problem. Any questions on this problem from one than last one for today? Wonderful. All right, keep mentioning your questions if you have any. Meanwhile, I'm going to put this last problem in the chat, and I'm going to share my screen with it so that you can read it from my screen, or you can grab it from the chat. This is a platinum problem, in fact, so probably around the level of newish gold, but it used to be a platinum problem when it was released. All right, so let's get into this. So this is if you played the game 2048, this problem is pretty similar to that one. So essentially, we got a number line of numbers, and we can combine two adjacent numbers. Okay, so let me just go straight to the document instead of writing it separately and then copying it over to the document. All right, so because we only have 15 minutes left, I'm going to try to be a little bit faster with this problem. So let's start by doing like a simple DP. Let's say we say something like DP, like left, right, so the DP is like arranged, the left and right, equals the max value we can make in the range. Now, the issue with this DP is that it gets really tricky to combine two adjacent states. Like, how do I combine this with another DP state? I don't know if the two can combine, if the edges could be whatever, right? Like, let's just say I have a range where I have the values like 1, 10, 5. And I have a DP state next to it, which is like 2, 6, or 2, 10, 4. So the DP for this is going to be 10, the DP for this is going to be 10, but I don't know if I can combine them, because there's stuff in the middle that's blocking. That's not going to work. So what if we just say DPLR is the value we get if we combine everything in the range? And the DP value does not exist if it's impossible to combine everything in the range. We'll say is -1 if it is impossible to combine everything in the range. All right, so now our start state is pretty simple. Just usually for range DP, the start state is going to be one value. In this case, it's going to be input of x. Just the x, the value in the array, is going to be the DP state. Our answer is going to be the max DP value. All right, now how do we do transitions? So if we're trying to calculate DPIJ, we're gonna basically combine two neighboring ranges into one. And like let K be the value that we're sort of splitting the range at. So if we're just drawing this out, this is gonna be like I here. This is gonna be K. This is gonna be K plus 1. And this is gonna be J. So transitions, we're gonna have DPIJ. So if there is a K, and again, we want K to be between I and J. So I less than equal to K is less than J. I can't be both K and K can't be both I and J because like K plus 1 to J is a range and I to K is a range, so it can't also equal J. Such that DPIK equals DPK plus 1J. So the left value and the right value are equal, then we're going to combine them. Then DPIJ equals DPIK plus 1. Pretty straightforward. Shouldn't start state be input x plus 1? Let me look at the problem again just to be sure. Why would it be plus 1, Pratik? All right, cool. Yep. All right, so no plus 1 there. All right, cool. So we have this as our transition. Wonderful. Now, what is the runtime of this? Oh, number of states. We have n squared states. Runtime or number of transitions per state. Well, we have to look through all possible k, and there's like O of n possible k. Times runtime per transition is just 1. And this will work for the gold version of the problem. For the gold version of the problem, n is about 200, so this works. It's about 250-ish or something. For the platinum version of this problem, this is going to be a little bit trickier. This is not going to work in short. So we have to do the same concept that we sort of did in the previous problem, where we're like, okay, the number of states is n squared. So while we have n squared states, it's going to be impossible to solve this problem faster than n squared. So we have to remove a dimension. Now, notice that a lot of these states are not even going to be like valid, because the dp value is -1 if it's possible to combine everything in the range. So, I mean, if you just like calculate the dp values that you used, it'll probably be pretty fast. Like the number of states will probably go down to about O of n log n. That being said, we're still going to have O of n transitions. So we're still going to have n squared. So we're not going to go into that solution there. Here's what we can say. The dp value equals the value we get if we combine everything in the range. What is the max sort of value we can get if we combine everything in the range? Well, we know that each value in the input starts between 0 and 40. So let's say our input array started out as big as possible. There's a bunch of 40s. And 40s. Okay, well, the first time we combine them, we're going to have a bunch of 41s. But only n over 2 of them, because half of them are combined. Then we're going to have a bunch of 42s. Only n over 40. 43s. And you can probably see where this is going. N over 8 of them. So, the max value we can get is going to be 40 plus log n. Because we keep halving these every time. And we can't, until we get down to, one item. And we're going to get down to one, we keep halving them every time, so we're going to get down to one item if we keep halving them in, log n times. Log base 2 of n. So, this dp state is only, it only can equal O of log n values. But there's n squared, states here, but it can only equal log n values. Whenever you're solving a dp problem, and this is, I've never seen a case where this rule is broken. If the thing that it equals has fewer distinct values than one of the dimensions of the state, replace the dimension of the state. That's always the trick that works in that case. Now, of course, you can come up with problems where it doesn't, but typically, whenever I've seen this trick has always worked. So, we're just going to switch these two states around. We're just going to switch R and the equal. So, instead of dp LR equals value we get if we combine everything in the range, we're going to say dp left side value of combining everything in the range equals the max possible value of R. Literally just switching these two dimensions. That's all we're going to do here. So now our number of states has dropped from n squared to O of n log n states. We made some immense progress just by doing this. Cool trick. All right, now what are our transitions going to be? dp. Okay, let's do our start state actually. So dp value and then whatever the input of L is just going to equal L. It's just a range of length 1. So instead of saying dp x equals input of x, we're going to say dp x input x here. X input of x equals x. So the range goes from L to R, so x to x, then is input of x. Our answer is still going to be the biggest. So now it's going to be the biggest value of x, such that dp Lx exists. The biggest value we can make. All right, now our transitions get a little bit interesting. So, nice, I agree. Yeah, this is a pretty cool trick. Now, from dp Lx, we have to try and combine it with dp. So the left is going to be dp Lx plus 1. Oops. So recall dp Lx equals R. So I have to combine it with dp R plus 1x, which is the same as dp of dp lx x. The reason I wrote it as dpr plus plus 1. And dprx is because it's a little bit easier to understand while we're just doing right plus 1x, right? So if we're just drawing it here, this is dpl, and this is like the value, we're combining this into a value x. And this is r. So now we have to combine it with r plus 1 with some range such that it makes x. So now our transition is basically going to be dpl x plus 1 equals. So we're going to take dplx and we're going to combine it. So we're going to check if dplx exists and dp r plus 1x, which is the same as dplx. Oh, this plus 1 should be outside of the dplx, and then plus 1 should be here. dplx plus 1 x exists. So if these two both exist, then dplx1 will equal to the right value of this. So it's basically it's going to equal to this. There's only one transition. So we have, so our runtime is now number of states n log n times number of transition. There's one transition per state times runtime of transition is 0.1. So runtime is n log n, and this works in time. Had this trick in educational at quarter DPE, still couldn't see. This is a decently common, not to say super common, but it's definitely something that happens quite often. And when it does, it's a really nice trick to get. All right, wonderful. This was the last problem for today. Thanks, guys.